Hello and welcome to the lecture series on solar PV system. In today's lecture we will be talking about maximum power point tracking in a solar PV system, and more specifically we would be looking into one of the widely used conventional method for tracking maximum power from a solar PV system, which is known as perturb and observe method. Okay, so it is also called it is one of the actually hill climbing method, and I will let you know why it is called hill climbing method after a short while. So let us start with discussing about the IV characteristic of a PV cell, and if these cells are connected in series to form a panel, and these panels are connected in series parallel fashion to form an array to obtain some useful power out of it for feeding it to load. So this is a typical IV characteristic, and these four curves actually show the IV characteristic at different insolations. Okay, so as insolation decreases, the curve is shown here with there is a significant change in the short circuit current. Okay, now we will take up a very simple PV system in which we have got a PV array, and it is connected to, definitely we cannot connect it directly to a load. I had told you that it is connected to a DC to DC converter, normally a boost converter. A boost converter looks somewhat like this. There is an inductor L, and there is a switch. This switch could be an IGBT or it could be a MOSFET. Then finally it is connected to the load. Here we are considering a resistive load of value R, and normally we connect a capacitor at the load side since we have to obtain a fixed DC output, and similarly we connect a capacitor at the input side also, call it C in and C out. Okay, now the values of this L and C in C out, they can be obtained by studying the dynamics of the circuit. Okay, so in order to understand how L and C are selected in a DC to DC converter, you can watch one of my video which I have made on a detailed video on a boost DC to DC converter. I would more specifically be focusing on selection of this load, which is resistive in our case, in this case, and then I will move to the technique perturb and observe. So this is your PV array. It is actually a combination of PV cells, PV panels in series and parallel, and let me also assume that it is receiving a uniform insolation. So by uniform insolation I mean that all the panels in this PV array are actually receiving same amount of sunlight. Okay, so maybe 1000 watt per meter square, or say 800 watt per meter square, or 600 watt per meter square, whatever be the sunlight irradiance, it is falling on the panel equally. Okay, Now corresponding to let me start with a short analysis, and let me take a new page. Let us consider a DC to DC boost converter with a battery as an input. Okay, we have V in as an input, then we have this inductor, then a switch, and then a diode. It is followed by a load R. I can actually uh, take a very simplified circuit. Let me take a simplified circuit, more simplified circuit. Let me remove this these inductor and this diode, just for analysis which I would like to present to establish what should be the load that we need to take for a particular PV panel. Okay, rather, or in other words, normally load is fixed and we have to decide what would be the specification or rating of the PV panel. For that, I want to just show some relation between R and the PV panel. So for that, let me assume that I have got this type of circuit. This is unrealistic, although just for sake of analysis I'm taking this. When this switch is connected, that means this source, don't consider it to be battery, let us assume that it is PV panel, since we are not allowed to short circuit a battery. Okay, so let us assume that this is a source which can be shorted, say for example if it is a PV panel. So if it is shorted, then the resistance seen by this source, what it would be? It would be 0. Okay, for how much time? For the time for which this switch is on. Let me call it T on. And say in the other case, suppose that this switch is now open. So when switch is open, that means this is the circuit. So now the load that is seen by this source is now this R. So R load is seen by the source for how much time? For the time this switch is off. Okay, now this switch is turning on and off at a very fast rate. So what would be the resistance or load that would be seen by this source? I can write it down. The average value of the load resistance that would be seen by the source, it would be, let me call it R equivalent. That will be given by 0 into T on plus R into T off divided by the total time for the operation of the switch. So that would give me R times T off upon T. And if I try to write the value of T off in terms of D, so it is 1 minus D times T. D is the duty ratio. T gets cancelled, so that means R equivalent is 1 minus D times R. R is the load. Okay, so, and we know that the duty ratio can vary from 0 to 1. Ideally it can vary from 0 to 1, although in a boost converter we don't go above 0.9 duty ratio. Why? Because we know that I've taken this topic in detail in my lecture on DC to DC boost converter, in which I had told you that a real boost converter, when we take its duty ratio above a certain value, then instead of increasing the output voltage, there is a reduction in the output voltage. Losses also increases significantly. So it is better to operate at a value less than 0.9. Okay. Anyway, for ideal case, we can assume that D can vary from 0 to 1. So if that is the case, so if I put 0 here, then this R equivalent, it becomes equal to R when D is 0. That means switch is always off. And if I take D equals to 1, then in that case the load becomes 0. So that means we can vary the load as seen by the source from 0 to R. Is it fine? Now come to solar PV. Now solar PV IV characteristic is something like this. Okay, for any particular insolation and temperature. This is IPV on the x-axis, y-axis, and VPV on the x-axis. So there is one unique point which is called the knee point. The knee point on this characteristic, where we have got the maximum power available from the panel. Okay, maximum power available from the panel. So let me call it this is, since inverse of the resistance, this is IV characteristic, that means 1 upon, let me call it R max. So R max is the value of load for which we can obtain maximum power out of the panel. That means if we have got a panel and we are connecting it to a load directly at which is having a value of R max, then we can obtain maximum power out of panel at a particular insolation and temperature. Okay, is it fine? So now our load is fixed and it may not be equal to R max. Okay, it may not be equal to R max, and moreover the panel characteristic is changing. This is also a problem. So you see here in this you see here the IV characteristic is changing, and yes, see here the voltage at which the maximum power occurs is different in all the 4 cases when voltage is changing. Okay, so R max for this curve is this one, R max for this curve is this one, R max for this curve is this one, and R max for this curve is this one. So R max itself is varying for different insolation. Okay, so what we conclude from here? Now we can vary R from 0 to R. R is the load. Okay, so that means this R required, this is 1 by R max, and this is the slope. So if we have got R max, we can only reduce R max. Okay, so that means we can increase the slope. So say for example, if we have got this this value R somewhere here, so this is 1 by R and it is cutting at this instant. Okay, so what we can do with this R, we can only reduce this, I mean R equivalent, this is R equivalent. So maximum value of R equivalent is R, and we can only reduce it. That means we can increase the slope. So this will go on the left side of this curve. Okay, so if we are going to increase the value, reduce the value of R, we are only shifting the load as seen by the PV panel to be 1 by R to be higher. Okay, in no way can are we going to reach this point. Do you understand? So that means we should have R equivalent somewhere here. 1 by R equivalent should be somewhere here, so that if we increase the slope, then we can reach at this maximum power point at some value of duty ratio D. Okay, because R equivalent is related to the value of R by this D, duty ratio. Okay, so that means we have to take a value of a PV panel such that we take into account this effect. Okay, so that means if we are having a load 1 by R value here, so we need to take a panel, an array rather, which has got a characteristic, uh, something like this. Okay, then only we can move from this to this point. Or and moreover, the variation of the curve because of the change in insulation should also be such that this line is always on the right side of this curve. Is it clear? So this point I was interested to make, and let me conclude here that we should have a PV system, and there should be a proper selection of the PV system for a particular load R. Okay, and 1 by R equivalent should always be less than R max. Okay, this is slope, it should lie somewhere here. Is it fine? So let us proceed, and now let us take up the algorithm itself. Okay, so now we are interested in tracking maximum power out of the PV array. So let me draw this PV panel, PV array, and let's have a PV characteristic somewhat like this. Okay, so this is VPV, and on the y-axis we have PPV, and this is the point of interest. This is Pmax. Fine. So how to design our PV system? So our PV system, it looks somewhat like this. We have a PV panel, and then there is an inductor, and then there is a switch, followed by a diode, and then we have a capacitor, and then we have a load. And load is resistive in nature. We have a capacitor here also. C in and C out. And these C in and C out are actually to ensure that the voltage out of the panel, the ripple is removed. Similarly, at the output also, the ripple in the output voltage is removed. While this part, this inductor, diode and switch is basically acting as the three components of a DC boost converter. Okay. So what is the logic of perturb and observe method? Perturb and observe. So what is the parameter that is in our control? And that parameter, if you say, can we change inductance? Can we change irradiance, no, these things are not in our control. Load, no, load we cannot change, it is fixed. So the parameter that is in our control is the switching frequency, isn't it? Sorry, the switching time. That means the duty ratio, the duty ratio D. So this is the parameter, this is the control parameter. So if I change this value of D, then I am actually changing the resistance which is observed by the panel, and consequently I can move from one point to the other on the IV characteristic and consequently reach a knee point. Fine. So, but what is the philosophy behind this perturb and observe? So, by perturb, I mean I will be changing this D. I will be changing this D and observing what is happening to the power output and the voltage output, the output of the output voltage of the panel and output power of the panel. So these things would be observed. Okay, and a decision has to be made whether we have to increase D or we have to reduce D. So that decision is based on the value of delta P and delta V. Okay, so you see here that if I try to draw one tangent, so the slope of this tangent would be positive, and if I draw a tangent here, the slope here would be negative. Slope is positive here and slope is negative here. So what is slope? Slope is basically dP upon dV, isn't it? If I'm talking in continuous waveform, for continuous waveform. But when we will go for discretization of this method, then we have to take delta P by delta V. Okay, average slope, not the instantaneous slope. So at this point, if I try to find out the slope, so what will be the slope? The slope is equal to 0. Okay, so what is the concept now? The concept is find out this slope. If it is positive, try to move forward in this direction till you reach the value slope equal to 0. Okay, and if the slope is negative, try to move on the left of the curve and reach the point where slope is equal to 0. Is it fine? So in computer, how we are going to do? So first of all, the logic is we will try to find out delta P. So delta P could be positive or it could be negative. So if delta P is positive, then now we have two cases for delta V. Delta V could again be positive or it could be negative, isn't it? So if delta P is positive and delta V is positive, what should we do with the duty ratio? Should we increase it or should we reduce it? Okay, to understand this, let me draw the duty ratio here itself. Let me erase all these things. Okay, and let me draw the duty ratio here itself. Say for example, okay, it's a bit thicker. Let me take a less thicker. Okay, so this is PPV and let this be the duty ratio D. So you see, if I try to draw the duty ratio versus the panel voltage. So duty ratio is varying from 0 to 1, and on the x-axis we have this VPV. So at the maximum value of VPV, the duty ratio is equal to 1. Is 0. Duty ratio is 0. While at 0 voltage, the duty ratio is 1. Very simple. Duty ratio 1 means the switch is always connected. That means PV panel is short. That means there is no voltage appearing across PV panel. While when duty ratio is 0, that means this switch is always open. This switch is open always. So that means short open circuit appears across the load or across the panel. So the output voltage is going to be VOC. Is it fine? So you see here, let us take the first case when delta P is positive. Okay. And delta V is also positive. So that means, let me take one line here and take another line. So by what is mean by delta V is positive? Delta V means calculating the value of voltage after perturbation and value of voltage before perturbation. So let me call it V after and V before. Okay, so definitely V after it is positive. That means V after. So V after would be here and V before would be here, isn't it? That's only why this is only way when delta V would be positive. After would be here. Okay, and power is positive here. Okay, so what I have to do, I have to move on this direction. I have to move on the right side of this curve. Okay, so what I have to do to move forward, I have to reduce this duty ratio, isn't it? So I have to go this side, I have to reduce the duty ratio. So that means D would be equal to the D previous value minus delta D, small perturbation which we would be doing in the duty ratio. And if it is the other way around, that means if the delta V is negative, so in that case what will happen? In that case okay, so in that case this is V before and this is V after. Okay, but other important thing is that whether we would be on the right side of the curve or on the left side of the curve. Since delta P is positive and delta V is negative, that means the slope of the curve delta P by delta V is negative, isn't it? That means we are on this side of the curve, this side of the curve. So that means I take two lines here, one line this one and one line this one, and delta V is negative. That means delta V after is this and V before is this, isn't it? So V after is here. I have to move back to reach this point, maximum power point, isn't it? To move back, what I have to do? I have to increase the duty ratio. Increase the duty ratio. Could see here. If I have to move voltage from here to this side, I have to increase the duty ratio. So that means D will be equal to D plus delta V, delta D. Is it fine? Similarly, if delta P is negative, then again we have two cases for delta V. It could be positive or it could be negative. Okay, so when it is positive, again, so delta P is negative. and delta V is positive. That means we are on again on this side of the curve, isn't it? But now VA is this one and VB is this one, because we are getting a positive voltage here. That means uh, delta V is positive. That means after, yes, this one VA is here and VB is this one. Okay, so that means uh, uh, after we are here, so again we have to move this side on this side. That means we have to increase the duty ratio. Okay, we have to increase the duty ratio. That means D will be equal to D plus delta T. Similarly, when delta V is negative, now delta is negative and delta P is also negative, so that means we are on this side of the curve, this side of the curve, positive slope. Okay, so in that case, again, if delta V is negative, that means V after and V before. So V after is greater than is less than V before. So that is when delta V would be negative. So in that case, we have again to move on the right side. Okay, so that means moving on the right side means reducing the duty ratio. So that means D will be equal to D minus delta D. Is it fine? So this is the logic how to implement uh, perturb and observe method. And now let me draw a flow chart, and then things would be more clear. So I will start. This is the start button. Then we move, and next step would be to initialize. So I'm trying to draw the flow chart for perturb and observe method in MPPT in a solar PV system. Okay, then I would actually be implementing this flow chart in MATLAB in Simulink environment. Although I would be using some MATLAB functions block in which some coding would also be there to implement this perturb and observe method. Okay, so I would be doing that in the next lecture. Here I would be restricting myself to the flowchart of the perturb and observe method. So first of all, we have to initialize what? The duty ratio D and the voltage, and normally we start with V equal to 0 and power and P equal to 0, and then we have to take the step of the duty ratio delta D, and we have to take some value. Let us take it equal to 10 to the power minus 4. Okay, so these are some initialization that need to be done. Apart from this, normally the minimum value of and maximum value of duty ratio is also selected. As I told you, we do not we try not to go above 0.9. Okay, so we try to keep ourselves within this duty ratio. So we will take this limit and try to force it on the controller, so that whenever it exceeds the value of Dmax, it is brought back to 0.9, and whenever it exceeds the value comes below 0.1, it is brought to 0.1 value again. Okay, so moving forward, so what is the next step? Next step is actually to calculate power PPV, and that is equal to IPV Let me call it uh, uh, starting value d start or v start. Similarly, p start. Okay, so IPV equals to VP, the new value of uh, uh, the power output PPV will be equal to IPV into VPV, because initially we have taken V start equal to 0 and P start is 0. Because V start is 0, so P start will also be 0, because it is product of V and I. But we will be starting with some values of D start, and let us assume that we start from 0.9 value. So when I put D equals to 0.9, then certainly the voltage and current is now going to be drawn. Voltage will be produced and current is going to be drawn from the PV panel. So the power that is drawn from the PV panel can be calculated by multiplying the product, multiplying these two quantity IPV and VPV. So we calculate it. VPV is IPV into VPV. Next step is uh, to calculate delta P. Okay, so delta P is equal to PPV minus PPV minus P start. Okay, so P start was 0 and PPV has got some finite value, so difference of the two is delta P. And we will also calculate delta V. Delta V is equal to, so V PV minus V start, the starting value. Okay, okay, or we can call it previous value, because we would be updating this. So start, don't get confused that start means this is only the initial value, but rather we would actually be changing this P start in the algorithm, in the flowchart. Okay, anyway, so next step is to check whether delta P is greater than 0 or not. So is delta P greater than 0? So there are two answers, either yes or no. So if yes, then well and good. So then the duty ratio D start would be actually the point where maximum power is available, isn't it? But if it is no, then what we have to do? Then, okay, sorry, just a minute. First is check is whether delta P is equal to 0 or not. So if it is 0, then we are at the maximum power point. So that means D equals to D start. If it is not equal to 0, then there are two cases. The first one is delta P greater than 0? Then we have two answers for it, no and yes. Okay, so when it is no, then I told you that we will check the status of delta V. Is delta V less than 0? Again we have two answers to it. Yes, if it is yes, I told you previously that D now will be equal to D minus delta D. Okay, or D start minus delta D. And if the answer is if the answer is say no, then D would be equal to D start plus delta D. Okay, and then in both the cases, okay, so and the other case is when delta P is not greater than 0, so that means delta P is less than 0. Here also we have to check whether delta V is less than 0. So we have two solutions for this case, whether no or the other one is yes. So for no we have D equals to D start minus delta D. Okay, and if it is yes, then D equals to D start plus delta D. Okay, so for both of these cases, then we have to move to one important constraint I told you, and that constraint is D greater than or equal to D max, or D less than equal to D minimum, this condition. Okay, so that needs to be checked. So in all these cases, say let me call it 1, this is 1, this is 2, this is 3, and this is 4. In all the 4 cases we have updated value of D. So it would be checking here whether that updated value is greater than D max or less than D min or not. Okay, so if there is no problem, if no, and it is not violating the limit, then what we have to do, we have to update the values of power. Now P start would be equal to PPV, and V start would be equal to VPV, and D start will be equal to D. So updating of the values, and then again it will go back to this step wherein the power is again calculated. Okay, did you understand this? And if this condition is not met here, D is greater than, if it is greater than D max, or if it is less than D min, then if it is greater than D max, then D is set to D max, and if it is less than D min, then D is set to D min, isn't it? So after this step back here. Okay, now here D start would be D start will be equal to D max or D min according to the violation of this condition. So I hope I have explained the flow chart for the perturb and observe method. So we will be actually implementing it in the next lecture in MATLAB. Thank you for watching.